Hello, good morning. Can you hear me?
Yes.
Perfect. So, thanks for joining us. Let me
Pleasure.
do the introduction and then we can start. Okay.
All right.
I'm delighted and honored today to introduce our speaker, Professor Yoshio Bengio. He's one of the key figures of AI and deep learning revolutions and machine learning pioneers. One of the three godfathers of deep learning and ACM Turing Award laureate. He got his PhD in CS from McGill University. He's professor at the University of Montreal and founder and director of Mila Lab. He's author of more than 250 publications with more than 200,000 citations. Co-curator and general chair of our ICLR conference. Co-creator, and co-author of a famous deep learning book, and also known for contributions like generative adversarial networks, GAN, RNNs, attention models, and many more advances in computer vision, speech processing. Another call. Speech recognition and text processing using deep learning. I wanted to make this introduction short because I believe that Yoshio doesn't need any introduction, and basically if you are deep learning researcher and haven't read any paper from him or haven't cited any paper from him, you should really reconsider your way of research. So Yoshio, I will let you to take over.
All right. So let me try to share my slides with you. Okay, now, do you see, what do you see? You just see me. Huh, strange. How about now? Do you see just one slide or you see the presenter screen? Okay, how about like this? Okay, good. So let me start. So I'm going to do a fairly broad presentation covering some of recent advances and principles and a lot of discussions about future directions. So first, let me share with you what really was my motivation in the mid-'80s to get really excited about neural networks. And still today, the reason why I'm so motivated by this work. The idea is that there's what I call an amazing hypothesis that maybe there are a few simple principles which can explain general mechanics from the observations and interactions of an agent with their environment. So learning, of course, is the main difference between the classical AI, rule-based, symbolic approach, and current AI based on machine learning. But it's interesting to also see some of the other differences. So, for example, the classical AI approach was based on the idea that knowledge would be provided by humans, either in the form of rules, facts, or programs. But unfortunately, that path didn't work because a lot of our knowledge is not something we can communicate easily. For example, if you think about common sense or your ability to perceive, this is not something you have conscious access to, and so you can't explain it to other people. You cannot explain it to a computer. Another important difference is how we handle uncertainty and probability. So this is something that was lacking in classical AI and is, of course, very present in machine learning. And finally, another big difference is classical AI was trying to manipulate directly the high-level concepts of the kind we manipulate with language. But it was not grounded in low-level perception and action, whereas machine learning, on the contrary, is really like more bottom-up approach, starting from perception and action. So to summarize, machine learning is one particular approach to AI based on learning, and it's succeeding because it's able to capture the kind of knowledge, intuitive knowledge, which classical AI failed to capture. And deep learning is a particular approach to this based on inspiration from the brain, based on the idea that the computation to be performed by the learner comes from the synergy of a large number of simple, adaptive computational units, which we can think of as neurons, but potentially in the brain maybe groups of neurons, like columns in the brain. Another really, really central approach, especially modern neural nets approach of deep learning, is the idea of what we call distributed representations. This was really the greatest idea coming from Jeff Hinton in the early 80s, and that he has pushed forward, and I have worked a lot on that. For example, my work on representations for words in the 2000s. So the idea of distributed representation is that it's the pattern of activation of neurons or artificial neurons, which represents the information rather than symbols. So for example, a word like cat would not be represented by simply one neuron turning on, but rather a whole pattern of neurons turning on, where different concepts would be represented by different patterns which may overlap. Also, the way that we think of how intelligence arises in machine learning, and especially neural nets, is by combining three ingredients. One is an objective function or a reward function. This is what we were trying to optimize. And then the other is how we optimize it. So this is the optimizer or the learning rule. And finally, we have to decide over what set of functions we are going to do that optimization and how we start the optimization. So this is the initial parameters, the initial architecture, as well as the family of functions that we are going to be exploring during the optimization. So this maybe a little bit caricature of how neural nets are conceived has, is much wider than neural nets and a very basic pattern of how things work in machine learning. Now, if we look at the success of deep learning in the last few years, I think we can draw some conclusions about some key ingredients that are behind that success. So number one, we need lots of data. Why do we need lots of data? Because in order to build an intelligent machine, it needs to have a lot of knowledge about the world. But that knowledge has to come from somewhere. And really, most of it is going to come from the data. Number two, in order to absorb that knowledge, the models need to have enough capacity. They need to be sufficiently flexible. So if you want, they need to have enough degrees of freedom, enough parameters, enough weights. Third, in order to compile the knowledge which is implicit in the data into the model, into the parameters of the neural net, you need enough computing power. This is something we were lacking in the 90s, for example. And then fourth, well, you need to end up with something that you can use efficiently, that inference, in other words, after you've trained and you use the system to answer questions, has to be computationally efficient. Some machine learning methods do not benefit from that. And finally, probably the most important thing is that when we want to solve complex problems, such as we have in AI, we are facing the curse of dimensionality. It's hard to learn and generalize properly in high-dimensional spaces. This is a central problem due to the fact that we're going to use a finite amount of data to train. And the solution to this comes in the form of assumptions or priors about the data distribution. So a lot of the advances in machine learning really are because we've proposed better assumptions or priors, which is like the principles I was telling you about earlier. To see why high-dimensional data is hard to model, think about learning to predict from a single variable that has only 10 values. You can just like count or average the values of the target for each of the 10 values of the one variable. And if you see, it doesn't take a lot of data to be able to populate that table, so that now you're going to have enough confidence about making a prediction for any of the 10 values. So that's fine if you have such a low-dimensional problem. But if you have, say, 2 variables, now you have to consider the 10 by 10 possible configurations of these variables. If you have 3 variables, it's 10 by 10 by 10, 1,000. And if you have 1,000 variables, which is not even that much, like you can have an image with 1,000 by 1,000 pixels, that's 1,000,000 variables. Well, the number of configurations is so large that there's no chance that you can have enough data for any randomly chosen new configuration. So it's hard to generalize. And the classical solution in statistics and some machine learning approaches like kernel methods to solve this problem was to assume that the target function, the thing you want to learn, is smooth. In other words, the information I gathered for one configuration, one of these little boxes, is approximately correct for the neighbors. Unfortunately, that doesn't work in high dimensions. And so we need more stronger priors to deal with that. And the general idea of how we deal with that in deep learning, and I think more generally over many machine learning methods, is to exploit what we call compositionality. In other words, the idea that we can combine little pieces together in order to form more complex models, more complex answers, sorry. This is something you can see at play in language, for example. And in deep nets, you can see it at least in 2 ways. So if you look at a single layer of a deep net, each neuron, each feature can be turned on or off. And if you have, say, n features, then you have at least like 2 to the n types of configurations, right? So you've got an exponential number of possible combinations. And the thing that's interesting is that you can learn from some combinations about the meaning of each of those features and then generalize to new configurations. So that's one form of compositionality. You also get compositionality by the depth of the architecture, by having many layers on top of each other, so that at one level the features are defined in terms of the features at the lower level. So this is another form of compositionality, which is akin to when you compose functions with each other in mathematics. Now, both of these require assumptions of compositionality about the world. In other words, it's all saying that an efficient way of describing reality is by composing little pieces together in a hierarchy and in parallel or in sequence. Maybe to understand the power of distributed representation, I can give this very simple 2D example. Let's say that your data is in 2D, like in those 2 pictures. Look at the left one, and you can try to understand what is going on in that data set by breaking the input into regions, like in one nearest neighbor or clustering. So now, in order to produce an answer for one particular region, you can average all the data points that come into that region. And potentially you can have a smooth boundary between the regions. So that's what a lot of classical machine learning algorithms do. But the problem with this is you need to have at least one data point per region in order to be able to say something about what the answer should be in that region. And so in high-dimensional spaces, the issue is that you really would like to have an exponential number of regions, and you'd like to be able to distinguish a very large number of regions, which is going to be much larger than the number of data points, just like in this example. So the solution, or at least one part of the solution that you get from distributed representations is shown on the right. So let's say you consider one hidden layer of a neural net with 3 hidden units. And each hidden unit is just like a linear classifier. It's going to turn on or off depending on whether the input is on one side or the other side of a linear classifier. So if you look, for example, at the black line, this might be indicating how one of the neurons, number 1, the hidden unit number 1, reacts. So if the input is above the black line, then it will output 1. If it's below, it's going to output 0. And similarly, if you look at the blue line, that might be the second neuron. If the data is below the blue line, then it's going to say 1, and if it's above, it's going to say 0, and so on. So now, by looking at the pattern of activations of that hidden layer, you can identify in each region you are, and then if you stick another classifier on top of this, you can use this for making predictions. But what's important is that the number of parameters that you need to describe the function you're learning grows linearly with the number of features. Here you have 3 features, and each needs whatever 3 parameters. Whereas on the left side, with the sort of partitioning approach, the number of parameters grows linearly with the number of regions, whereas on the right side, the number of parameters grows as the log of the number of regions. So you can have a much more compact description for a large, complex function. So a function may look complicated, but if it satisfies this sort of compositionality assumption, it can be represented very efficiently. And to see, what kind of assumption that means, imagine you had a neural net, like a convolutional net, like in the picture, which processes images of people. And then at some level in the hierarchy, the hidden units, let's say we were to imagine what they could be doing. So imagine there would be a unit that would detect whether the person wears glasses, and another unit which would detect whether the person is a female, and another unit which would detect whether the person is a child, and so on. So now you can see that the number of parameters you need grows no more than linearly with the number of these features. However, if you were to use a more classical approach, and you want to be able to generalize to any configuration of these features, you would need an exponential number of examples. So with the neural net, you need like a linear number of examples. With the sort of nearest neighbor and kernel methods, you might need an exponential number of examples to basically say the same thing. And the reason it works here is that you can learn about what it means to wear glasses without having to consider all of the exponential number of configurations of the other features. Right? So I can build a glass detector, and it doesn't need to be trained. It doesn't need to see all of the different configurations of whether the person is a child, a male, a female, and so on. So that's the trick. So to summarize, a crucial idea of deep learning is that we're going to learn these internal representations that capture meaningful aspects of the world. Now, this begs the question, how do we know what is a good representation? How do we train it so that it discovers good representations? And a general intuition is that good internal representations should make downstream tasks easier. So of course, if you train them in a supervised way, this may happen. But we might also want to be able to use unlabeled data to discover these representations. And so we need to think a bit more about what we would like to see from these representations, in particular the highest levels of representation. Because an important idea of deep learning that we put forward about 12 years ago is that we want to learn multiple levels of representation where the higher levels correspond to more abstract concepts. And why do we care about abstraction? Because abstraction allows you to generalize more easily, to make predictions in a more general way. and to transfer, for example, to new distributions more easily. So there's this notion of disentangling factors of variation, that the representations at the top level should be such that they can easily predict, say with a linear classifier, any of the high-level concepts that we care about, of the kind that we communicate with language. So now if we look at what deep learning has brought us, it's brought us pretty amazing progress in AI in general. But if we look a bit more carefully, we see that most of the progress has been with perception. In other words, the ability to transform high-dimensional objects like images into categories. What is in the image? But actually, there's been also pretty substantial progress on the side of language. For example, in the picture here, we see a system that's been trained to produce a sentence from an image. There's also been progress in playing games, like the game of Go, you probably heard about, and reasoning. But language and reasoning and things like this, we're still, I think, far from human-level abilities. And I'll come back to that. So a little bit of the history of the progress. Really, one of the first application areas of deep learning has been speech recognition. And it took really very little time from the first results in labs to products, about 2 years, around 2010, 2012. And then came the breakthroughs in computer vision, which had a much wider impact. In a matter of 1 year, the improvement of deep learning over the classical systems was such that pretty much all of the participants switched to using deep learning. And then over the years, it had continued to improve, reaching in 2015 human-level performance, at least in terms of numbers, in terms of accuracy. I don't think we have computer vision systems that are as good as humans by far. If you look at the kinds of mistakes that are made, they're very different. Humans make mistakes because they don't know maybe some category, whereas machines make still pretty stupid mistakes, which reveal some of their limitations. Now, one of the things, one of the lessons from the ImageNet competition that I just mentioned is that I think maybe sometimes overlooked is, I think one of the reasons why it's been working so well is because we had so many categories. So in the ImageNet competition, there's 1,000 categories, right? And about 1 million examples. So that's about 1,000 examples per category. Now, if you were to train a ConvNet with 2 categories, with like 1,000 examples for each category, actually it doesn't work that great. But if you train it with all 1,000 categories, suddenly it works well for pretty much all of the categories. So what's happening is that there's a synergy going on. There's a sharing of information between those tasks. Of course, because like recognizing a cat and recognizing a dog calls upon lower level features that are shared across these 2 tasks. In fact, that are shared across many tasks. And so the architecture shares all of the layers up to the parameters of the last layer, which are different for each category. So this idea was older, of course, and I think is an important lesson of the success of deep learning. And again, it relies on an assumption that each task reveals a different aspect of reality, but that the underlying reality is shared across all the tasks. So, what did I have to do with deep learning? A lot of papers and so on, but maybe to try to highlight some of the things that today have a large impact. The early extensions of neural nets are the things that allowed us to really increase the depth of these neural nets. Before 2006, we didn't really know how to train deep ones. And we came up first with methods based on stacking autoencoders and RBMs. And then we realized that we could get the same thing much more easily by replacing the nonlinearity that used to be hyperbolic tangent and sigmoid with ReLU, with piecewise linear nonlinearity. And we also found that initialization was important. So very little things really made a big difference and allowed the progress in deep learning to move forward very quickly. Another sort of broad area of progress is how neural nets of this century have, especially after 2014, have moved beyond classical pattern recognition. So in the 90s and 80s, people were thinking about neural nets as pattern recognition machines. You take a fixed size vector and you output a category. But in recent years, we've seen that little mental picture really change a lot. First of all, we can now generate images. So basically, we turn this neural net upside down, and it takes, if you want, say, category as input, and it produces an image. And the biggest success in that has been the GANs, the generative adversarial networks, that I'll mention a bit more. But it started with our work on autoencoders and denoising autoencoders and self-supervised objectives, which are still like a very active area of research. And then another really important change from the earlier times is the introduction of attention mechanisms. And that has made it possible to generalize from processing vectors to processing essentially arbitrary data structures, graphs, sets, any data structure. And finally, another really fundamental progress in the last couple of years, but dating back to earlier work I did in the early 90s, is meta-learning, where we are rethinking the objective by which we're training these things so that we can actually optimize for generalization. We can optimize for transfer. So let me say a few words about attention. The need for attention came in our work on machine translation. In fact, we started working on this in 2014, and by 2016, these ideas have been put in the Google Translate and led to a huge improvement in the quality of translation from previous systems which were based on n-grams. So the motivation in machine translation is that we wanted to be able to use a recurrent net that produces the answer, which is like a sentence in English, one word at a time, so that as it produces one word at a time in the output, it has the ability to go back and look at the specific words that were used as input for the sentence to be translated. And for this, we needed a kind of attention mechanism which can focus on one element of the input sequence in fact, arbitrary order, because, for example, when you go from French to English or English to French or many other pairs of languages, the order of the words is changed. And so we need to be able to look back at any past position. So this ability to focus on an element in a set is really what allows modern deep learning to work on any data structure. And the other big thing about these attention mechanisms is that they're what we call soft attention. So they're differentiable. They don't actually put all of the focus on one element. It's distributed across all the elements. But using a softmax usually converges to something close to focus on one thing. But while it's learning, it has a chance to figure out how to put attention, where to put attention. It turns out that attention is now being used for systems that have memory, because you can focus your attention on different memory elements. It's also allowing to deal with long-term dependencies, because you can focus your attention on past elements of a sequence, independent of how far they are in the past. And they really form the basis of the current state of the art in many natural language processing tasks, using what's called transformers and self-attention. And finally, it's connected to consciousness, which is something that people are starting to think about in machine learning. Because when you're conscious of something, you're focusing your attention, again, on a few elements. So the GANs have led the progress in deep generative models in an amazing way. What you see on the top is the progress over the years in generating images of faces. So actually, all of the images you're seeing there are synthetic. They're not real people. They're not real images. They were imagined by a neural net. And you can see on the top row how, the progress from 2014, from our first paper, every year how much we're getting, more and more realistic, to the point where it can be scary and actually could be dangerous if it's misused. Also, we can train what we call conditional GANs. So it's not just generating from some distribution, it can do it conditioned on some input. So in the bottom right, what you see is we're generating the image of a bird given a descriptive sentence, like this bird is red with white and has a very short beak. That sentence, you can type any sentence and it will influence the image that is generated. Another really cool thing that has happened around GANs is what's called cycle GANs. Let me see if the video works. Yeah. So in case you haven't seen this video, what it shows is that a system has been trained to map images of horses into corresponding images of zebras. And you can see that the horse now has all those stripes, but also the grass is brown because zebras usually live in Africa. So it has changed the whole image to be consistent with a data set of zebra images. So what's going on here is that you learn a two-way map between one domain and the other domain using only images from each distribution, from each domain. So it kind of figures out a relationship between the two distributions that is as simple as possible, such that when you take an image of a horse and you apply the encoder, you get an image that looks like coming from the distribution of images of zebras. And you can imagine how this could be used, for example, in machine translation, and it is being used. If you have very little data of paired sentences like English and French, you have a lot of data in English, a lot of data in French, but very little pairs, right? So in fact, here it uses no pairs. If you have a little bit, you can do even better. Something related to all this unsupervised work is self-supervised learning, which is basically an idea to define objective function for unsupervised learning, where you predict part of the data or functions of the data from other parts. We started doing this kind of thing with denoising autoencoders around 2008, but modern natural language processing systems based on unsupervised pre-training, they make a heavy use of this idea. Pretty much all of the state-of-the-art systems to learn word embeddings use self-supervised learning. However, I think where we're going with self-supervised learning is instead of predicting in the data space, we can predict in the space of representations, in the latent space. So what you see in the picture is two images from a Atari game, and we're trying to learn good representations in an unsupervised way. So we're learning this convolutional mapping that goes from the input image to a spatial representation and then through dense layers to a non-spatial global vector of features. And instead of predicting what the pixels would be looking at the next time step, we're training this thing to predict what the latent features would look like at the next time step. Now, if we were just optimizing prediction, we could find a trivial solution where it learns to predict a constant. Well, that's easy to predict. So instead, we are exploiting recent work in neural nets to maximize mutual information between representations. So I'm not going to go into all the details of this, but this allows to learn representations that capture information about the input and are predictive of each other. Okay, so now I guess we're transitioning into a little bit of a discussion about the limitations of current systems with the idea that we start looking a bit more forward where we would like to go in the future. So the current progress in deep learning is mostly in the kind of task that psychologists call system one tasks. Tasks you can do quickly, sorry, that you can do in an intuitive way. For example, perception tasks. But these are tasks that are happening in the unconscious. It's hard for us to explain in sufficient detail how we can recognize an object, for example. So deep learning does these things very well, but what it's not so good at is system 2 tasks, things like reasoning, things like coming up with an algorithm. And these are computations that are happening in a conscious way. So if I ask you to add two numbers like 34 and 46, you can probably do it in your head by going through steps in your mind. And that takes a bit of time. You can explain how you do it. You can explain it to a computer. That's what programming is about. It's a very different kind of computation. This is the kind of computation that classical AI was trying to do, but it was not grounded in the sort of low-level system 1 type of computation. So in the future, we need to build systems that can have both of these things. And one of the important messages I'm giving in many talks is, whereas the system 2 tasks are more closely connected to language because it's about things you can explain with language, we shouldn't be trying to learn these kind of tasks in isolation, like NLP systems that are trained only on texts. In order for language understanding to work, we need the learner to be exposed not just to text, but also to what text refers to, right? So it needs to understand how the world works, which is really something happening at the level of system 1. So combining the two right now, you can look, for example, at what's called grounded language learning, where you may combine sentences and videos, for example. All right, so if we look at the current successes in machine learning, especially in industry, it's mostly based on supervised learning and requires a lot of human-labeled data. And it's the human, by providing the labels, which give to the machine the important high-level abstractions, like the names of categories. But if you don't provide those labels, the systems are not able to discover these kinds of high-level concepts by themselves. Also, even with supervised learning, if you look at the mistakes made, they reveal that they make very different mistakes from humans that don't generalize very well out of the training context, and they can be fooled very easily. For example, in the picture, we see a system that's been trained to recognize images from ImageNet, and it's going to say that the image on the left is a dog, but we can fool it by modifying the pixels a little bit, and you don't see the difference, but on the right, the image is slightly different, and it's going to say ostrich. So these are adversarial examples that for which we don't have a complete understanding yet, but basically, in my mind, it reflects a lack of sufficiently abstract understanding of images or whatever it is that the system is trying to understand. And so I think we need to do a better job at building systems that have a kind of common sense understanding of the world. And it's an understanding of the world which, for example, children, like a 2-year-old child, can obtain in a completely unsupervised way. So if you think about intuitive physics, in other words, like a child understands gravity, understands after like a year or a year and a half, understands gravity, understands forces, understands solids and liquids. This is intuitive physics. The child doesn't have like equations in their mind. They have built an intuitive understanding in system 1 of how physics works. And it's not because the parents have taught them, right? It's been done in a completely unsupervised way by observing the world and interacting with it. So we need to make progress at unsupervised learning to build this kind of learning ability that we find in children. So this ability to understand how the world works and to figure it out by exploring it is something that we need much more research on. And one of the aspects that is really lacking currently in machine learning, something that humans can do very well, is understanding how the world works through causal relationships, right? So it makes a huge difference to know that It's the rain which causes umbrellas to be opened by humans. If you open your umbrella, it's not going to make the rain come, right? So the causality is related to the notion of agency, the notion of acting in the world, right? It doesn't make any difference whether A causes B or B causes A if you're only observing the joint distribution of variables. But if you're going to be an actor, if you're going to be doing things in the world, it matters a lot, because if you're trying to make the rain come by opening your umbrella, it's not going to work. Whereas if you are able to make the rain come, it's gonna create people opening up their umbrellas. So the direction of causality is something important as soon as you have a learner which interacts with their environment and acts in the environment and wants to be able to plan and take decisions that yield some results. So one big problem is we don't have these high-level causal variables like rain and umbrella. We would like our learning system to discover them, just like babies do. And so they need to go from low-level stuff like pixels and images to these high-level representations. So this connects to the earlier discussion I introduced about abstraction and disentangling the underlying factors. So these underlying factors don't need to be statistically independent, but what I claim is that there's going to be a fairly simple form of dependency between them, which I call the consciousness prior, where only a few variables at a time interact with each other. But there are other clues that we can use to learn high-level representations, like the presence of spatial and temporal scales, and how we act, how the effects of what we do influencing things in the world. So let me say a few words about both the consciousness prior and the influence we can have in the world. So one of the ideas in the consciousness prior is that at the high level, we want to have two kinds of states. We're going to have like a high-dimensional state, which contains all of the concepts we could think about. And then there's a conscious state, which is a much smaller object, which selects using attention a few of these things at a time, which go into your consciousness. At the next moment, it might be a different thing. But there's this focus, and this focus allows to put together a few concepts that are interrelated. You can think of that like forming a sentence. So this is the form of the interactions between those variables, involving a few variables at a time. The other idea about high-level representations is that for humans and animals and probably for robots, we would like many of these factors to correspond to aspects of the world which we can control, which agents can change. Right? So this is an old idea actually in psychology called affordances. The idea that the way that we represent objects in the world in our mind has to do with what we can do with them, how we can change them. So there's been some work starting a couple of years ago to go in that direction, exploiting again the idea that we can use neural nets to learn representations that maximize mutual information between them. So we can maximize mutual information between intentions, like I want to move the table, and what happens in the world, in the state of the world, and how it's represented. So if I intend to change the position of the table, then there should be some aspect of the world which represents the position of the table. So that, like, there's a natural relationship between the intentions and policies on one hand, and the different aspects of the world which can be controlled independently. In addition, there should be a kind of intrinsic reward for being able to control things. So this is like an unsupervised objective, which agents have. If you think about babies, they're always trying to control their environments, control their parents, for example. And it's like a natural thing. We need to be able to control our environments, independent of the task. Now, reinforcement learning, which I believe is one of the most important directions of expansion for future work in AI and machine learning, currently suffers from a problem of what we call high sample complexity. The systems, for example, to play Go and so on, or Atari, they need a huge number of examples compared to what a human seems to need to learn the same thing. My research direction to address that is, along with other people, anchored in the belief that we need to combine current approaches in reinforcement learning, which are what we call model-free, which don't explicitly capture how the world works, with model-based approaches, which have some sort of representation of how the world works. So that we want to be training agents which can simulate possible futures, but using generative models that can project us into the future, not in the pixel space, but in the abstract space, in the latent space. Okay. The last bit I want to mention before I'm going to let you ask questions comes back on this notion of causality. So in the last year, we've been starting to explore how meta-learning can be used to learn about causal representations and causal relationships. So what we would really like is for our high-level features to correspond to causal variables. But you have to realize that not all variables are causal. So a causal variable is a variable that can be part of a causal relationship. So it could be the cause or it could be the effect of some interaction, right? But many variables, like say pixel values, are not causal. There's no like natural causal direction between two pixels. A pixel does not cause another pixel, but the rain can cause umbrellas to open. So a big question here is, how are we going to learn a mapping from the observed data, like pixels, images, to these high-level variables, and how do we learn the relationship between those variables, like which is cause and which is effect? And they seem like very simple questions, but we don't yet have very satisfactory answers. So I'm not going to have time to go through all the remaining slides, but I want to mention this paper that we put out on arXiv recently called the Meta-Transfer Objective for Learning to Disentangle Causal Mechanisms, where we try to exploit changes in distribution, the fact that the world changes, there may be different environments that the learner goes through, and seeing this not as a bug, because it makes it harder to generalize, but as a feature, because it provides information about the parts of the world that are stable, like causality, and the parts of the world that can change, that have to do maybe with a particular intervention that happened that changed the value of some variable. Where he said, nature does not shuffle environments, does not shuffle the data. We should not. And the reason he's saying this is that when we shuffle the data, which is the standard way that we are doing machine learning these days, we make the data IID. We lose information about these different sub-distributions, these different environments that actually can teach the model about the aspects of the world that are stable, that are invariant across environments, and things like causality is one of these things. Okay, so the last thing I want to mention is sort of a non-technical comment. For many years now, a lot of the effort in machine learning has been to help companies build the next gadget, the next app on your phone. And this could be, very much fun and can make a lot of money. But I think that as scientists, we have a responsibility to think beyond just the profit motive and think about how our technology is going to be used. First of all, we have to realize that it could be misused. For example, in military applications or to control people with advertising. But it could also be used for good, not just through profit-making applications. So, for example, it could be used to help in humanitarian situations. It may help to fight climate change. It may be used to improve healthcare or education. So I want to mention this organization called AI Commons that we have contributed to create, which aims to coordinate projects in AI for social good applications and help people to connect, people that have maybe knowledge about an application and data, and people who have knowledge about machine learning, or people who have money to fund these kinds of things. All right, I'm going to stop here and answer your questions. Thank you.
Okay, thank you, Joshua. We received a couple of questions. We just picked
Yeah.
up a few of them. I think we have 10, 15 minutes to do Q&A. So the first question is what's the next new trends of waves of deep learning for, let's say, for next few years?
Do you see me now?
Yes.
Okay. Well, I mean, the second half of my talk was all about this. So to summarize, I think that we will see more and more work combining deep learning and reinforcement learning. The agent perspective, I think, is very important in machine learning. So in the past, we've been focusing on static data where the data set is collected once and for all, and there's no interaction between the agent and the environment. And the reason I think this is important is, I mean, if we want to move towards systems that actually understand the world, the agent perspective allows to capture things like causality, allows to capture how things change in the world in a way that is much more difficult with pure observation from a single data set. Another thing I mentioned quickly is I believe that the work in natural language, which is pretty amazing and has a lot of applications already, is kind of saturating because we are training just on texts. And even if we use like huge, amazing quantities of text, we end up with systems that still don't understand very well what they're talking about. And the reason, as I said, is because they don't have a good world model. So until we make progress in systems that actually understand their environment, learn to understand their environment, explore their environment, I think that the progress in natural language understanding is going to stall. Another related area is this system 1, system 2 thing. So up to now, we've been focusing a lot on perception, which is great, but there are a lot of aspects of human cognition that we're still missing. So, and then finally, I mentioned meta-learning, which has been around for a long time, but it's really only in the last couple of years we've seen pretty exciting progress. And for me, it's like a game changer because it allows to train towards better generalization as well as better robustness to changes in distribution, which is the thing where, like, even in most industrial applications, we see that current systems fail when you, say, train them on one city and then test them in another country. You see the performance degrades considerably. But now with meta-learning, you can train a system so that it will transfer more easily to a different distribution. So these are some examples.
Okay. And one more question is that some AI researchers believe that deep learning is really costly in comparison to the achievements. Do you agree with this? Or if you're not, do you have any sense about finding a simpler or more powerful, less expensive learning algorithm in the future?
Well, it's hard to put on the same scale the benefits of things like deep learning, which are amazing, and the computational cost. So clearly, in dollars, the benefit of deep learning is hugely superior to how much it costs in terms of computations. I mean, that's why companies do it, right? So clearly that statement is wrong from that point of view. But the other thing I want to mention is that there's a lot of effort currently in companies like Intel and other like chip builders to create deep learning hardware that's specialized for deep learning and is going to be much more efficient in terms of energy consumption. So I've worked a little bit on these things. And I think it's going to bring multiple orders of improvement in speed and power consumption in the next few years.
Okay. Okay, one question. Many believe that we are approaching the end of deep learning era. Well, what do you think of that? Would the deep learning be along with the machine learning specialists until the technological singularity?
So first of all, I don't believe in the singularity. I think it's not a meaningful statement because science progresses by small steps. And regarding deep learning, I think a lot of that is people who have been working on different areas of AI and maybe feel frustrated because they're not getting as much attention as they used to. But in my mind, the way science works is we build upon the concepts that we have learned. So there's a toolbox of concepts that we have discovered with deep learning. And I think many of these concepts, especially the more central ones, are going to stay. Of course, the algorithms will change, and we need to go beyond what we have because what we currently have has limitations, as I try to explain today. But I think we will just, put more things in the box. For example, what I'm working on is being able to tackle system 2 tasks using deep learning, right? So we can start doing things like reasoning and planning using deep learning. That's of course my opinion. I don't have a crystal ball.
Okay. One question about the probabilistic approaches. Do you think that the Bayesian networks, Bayesian approaches can help deep learning more? So deep learning, the algorithms of deep learning, they need a huge amount of data. And do you think that the Bayesian network can help with that? To reduce the amount
possibly.
Of the data? Yeah.
I mean, there's already a rich history of interactions between Bayesian approaches and probabilistic approaches and deep learning. In fact, the early days of deep learning were based on graphical models. And I think there are places where the Bayesian approach can be quite interesting. For example, if you think about an agent which tries to explore their environment, they want to go in places where they lack knowledge, right? Because they want to go in places where they will learn. In order to do that, you need to have not just knowledge, but also knowledge of, what you don't know. Like what is my the limits of what I know, so I can explore at that frontier, right? So Bayesian approaches can be used to represent the uncertainty in your knowledge, and I think this might be an important ingredient.
Okay. One question about the adversarial attacks. Deep neural networks show excellent results in image classification tasks. However, they're vulnerable to adversarial attacks in which our brain is not weak. Do you think it stems from the lack of information, which is neural net, or what's the roots of this problem, and how can we fix it?
So first of all, I don't think that it's something specific to neural nets. Even humans are, can be fooled, right? You have visual illusions. You have in politics, you have demagogy, right, where people get to wrongly think something through some kind of influence. Advertising is controlling your mind, right? I mean, so like we are full of vulnerabilities as humans, and the problem with adversarial examples can be shown in other machine learning approaches. So I think it's the basis. The reason why we fall for and these neural nets have these failure modes is because the model is imperfect, right? Any imperfect model can be fooled, and so there is no like a foolproof solution. We have to improve our models. We can make them more robust. we have to make them able to understand the world in a deeper way, in a more fundamental way. This is why I've been talking so much in this presentation about high-level representations and abstraction.
Okay. Do you have any comments on the capsule nets presented by Jeff Hinton? For example, it can be the same story with what happened with the Jan LeCun's conv nets that happened after like a couple of decades. And do you believe that it can happen the same thing with the capsule nets?
I don't know, maybe. I can tell you that he's been like working really hard at this for about a decade now, and I trust his intuition. Now, personally, I think there are some interesting ideas. So there are things I like and things I don't like about the work that he has done around capsules. So on the one side I don't like is that he wants to use some very specific features of graphics and in order to design the structure of his capsule nets. But what I like about the capsule nets, and I think it's a very important aspect, is grouping a few neurons together into one capsule so that the capsule, like this group, really takes a meaning as a group. And it makes a lot of sense. If you think about objects, right? Objects are entities that have a bunch of attributes. So we want to group together these representations of objects. So I think that's on the right path. How we represent objects in neural nets right now, I think, is not satisfactory. And capsules, maybe one interesting direction towards this. Personally, I think we need to add to this notions of attention, right? Because when we start speaking about objects, we have like a set of objects, and the set can change depending on what we're seeing. So manipulating elements in a set where each element might be a capsule, I think, is the direction we should go to build systems that can really do the right kind of computation for object level cognition.
Okay, I think we just have 2-3 minutes. The last thing that lots of people ask about is, do you have some specific recommendation for the research topics for your young researchers?
Yeah, I mean, that's what I've been talking about today,
sure.
Right? You also have to open your mind, read a lot of things, make your hands, put your hands.
Oh, shoot. کانکشن رو مشکل داره. بله بله شه. کانکشن خودش مشکل داره.
And it doesn't work. It doesn't behave like you think it should. Maybe it's actually interesting. Like, so negative results could be sometimes very important in science. Don't just ignore them.
Okay. That was the last question. Thank you very much for your time.
You're welcome. Have a good day.
You too. Bye-bye.
Bye.